You have heard this a lot. AI models like ChatGPT run on thousands of GPUs. Companies spend billions of dollars on them. We need entire data centers just to keep them running. The usual explanation sounds simple. It's for speed, for scale. More people are using AI, so we need more GPUs. That makes sense. But what if there is only one user? No other traffic, just you. You sent one message and now waiting for a reply. Even then, one GPU is not enough. Not because it would be slow, because today's frontier models often cannot even fit on one GPU. And the reason comes down to one thing: memory. Before an AI model can answer anything, it first has to fit inside the GPU memory. At its core, an AI model is just a huge collection of numbers, billions of them, called parameters. Each parameter is stored in memory, taking about 2 bytes. That sounds tiny until you multiply it by billions or even trillions. GPT-2 had 1.5 billion parameters. GPT-3 jumped to 175 billion. And today's frontier models go even further. At that scale, those tiny numbers become hundreds of gigabytes. A 175 billion parameter model alone takes around 350 gigabytes of memory just to store the weights. And even a high-end GPU like NVIDIA H100 only has about 80 gigabytes of memory. So even to load the model, we need multiple GPUs before it can give any answer. But the weights are only half of the problem. When you send a message to ChatGPT, the model does not just read your last sentence. It reads the full conversation, your earlier messages, its previous replies, all the way back to the start of the conversation. And that's harder than it sounds. Take a sentence like "it was tired." Here, the model has to figure out what it refers to. To do that, it looks back at everything that came before and decide which parts matter most. That process is called attention. And attention is expensive, because for every new token it generates, the model has to compare it with all the previous ones. To avoid doing the same work again and again, the model saves part of the attention work it has already done for previous tokens. Those saved pieces are called keys and values. Together, they form what is called the KV cache, and they also sit in GPU memory. But the problem is, KV cache keeps growing. Every word you send and every word the model replies, all of it accumulates to the KV cache. So a short conversation, that is manageable, but a long session is different. Think about an AI coding assistant. You are not giving it one file. You are giving it an entire code base. Hundreds of files, documentation, dependencies. Context like that can reach hundreds of thousands of tokens, and at that scale, the KV cache alone can take tens of gigabytes. That is on top of the model weights that already did not fit in one GPU. So the memory requirement at the start of a conversation and an hour into it can look completely different. The model itself has not changed, but the memory it demands has. And as the conversation grows, that memory keeps growing too. So now we have two problems. The model does not fit in one GPU, and even if it did, the memory demand keeps growing while it runs. At some point, you run out of space. So the only practical option is to divide it across multiple GPUs. You take the model weights and the KV cache and distribute them across machines. Now the model finally fits. But once you do that, a new problem shows up. Imagine working on a group project. You divide the work so it gets done faster, but now you also have to coordinate. You wait for someone else to finish their part before you can continue yours. And the more people you add, the more coordination it takes. GPUs face the exact same problem. If the model is divided across machines, no single GPU has everything it needs. So at every step, they have to exchange data, back and forth, constantly. So the bottleneck moves. Before the question was, can one GPU hold the model? Now the question becomes, can many GPUs pass information fast enough to behave like one machine? And that is the cost of dividing the model. Once it is spread out, every answer depends on how quickly those pieces can communicate with each other. So what started as a memory problem became an engineering problem. And that engineering problem now sits at the center of modern AI systems. The model does not fit, the memory keeps growing, and once you spread the model across GPUs, the bottleneck moves, not disappears. Each problem creates the next one. There is no simple shortcut around it. And it does not stop here. Today, models are getting larger, contexts are getting longer, systems are handling entire codebase, running for hours, holding more in memory than we could have imagined just a few years ago. The limits are still there, we just keep pushing them further. So we did not choose to use hundreds of GPUs because it sounds impressive. The problem forced us there.